All right, let's take a look. Lesson 2-4. I can construct a model for situations involving proportional output values over equal length input value intervals. So what are we doing today? Someone translate that for me.
We're making the table.
We're going to be making tables. Very good. But it'll be more than just tables. What else?
Graphs.
Okay, that's not the word they're using. What are we looking for? We're going to be creating a function. What made you think creating a function? Model. When it says create a model, that means we're creating a function to represent data. Okay, so it says sometimes from the data from an exponential function does not display proportional growth pattern. This is due to a vertical translation. It's due to a what?
Vertical translation.
Now you might remember last class we dealt with a lot of different things, but among more things than not, last class we saw a horizontal transformation. Let's say 2 to the power of x minus 3 become a vertical dilation or vice versa. So last class we had something like this become, what could that be equal to? 2 to the power of x minus 3 we said is the same thing as using the quotient rule. 2 to the power of x over 2 to the power of 3, which we could rewrite as 2 to the power of x over, what's 2 cubed? 8. And then finally, the way we would finish is we would rewrite it as 1/8 times 2 to the power of x. So last class we learned about horizontal translations becoming vertical dilations or vice versa, a vertical dilation becoming a horizontal translation. Is that what we're doing today? Now, what's that say there? Vertical translation. We're dealing with vertical translations today. So it says, however, we can add or subtract a constant, and from the output values, we can come up with an exponential equation. That's basically what we're going to do today. So this one's some people are going to pick this up probably really fast and think this is easy. Others are going to be like, I don't even know how you would start this. So for those, I'll give you a hint and a little bit. Let's look at this first table here. And remember when we started this unit, we started with arithmetic and geometric sequences, and we said geometric models, what type of functions? Geometric models exponential. And so the formula I gave you for that was Gn equals
GK times R to the power of n minus k.
Okay, y'all are doing great. Y'all are doing great. And I'll put that in parentheses there. The R, the reason I pulled this up is I wanted to remind you what the R formula was. R was you take any term. No, that's for common difference. You take any term and you divide the one that came before it. Okay, so for example here, you would take 13 and divide by 7. So what is 13 divided by 7? Can that be reduced? No. Okay, so then you would try the next one to see if you get the same thing. You get 25 divided by 13. Now, can that be reduced? So I'm looking at the common ratio here. They can't be reduced. Are they equal to one another? Is 25 equal to 13? Is 13 equal to 7? No. But you probably can pick up what our rate is going to be approximately by using a limit. We're going to get closer and closer. Let's try this next one. We now have 49 divided by 25. Is that the same as either of these two? So right now we don't have a common ratio. Are you tracking with what I'm saying? I'm trying to show you. Do we have a common ratio right now? No. But we can predict what that ratio should be. I'll do one more. I have 97 divided by 49. Okay, here's what I want you to do. With your calculators, I want you to type these in and tell me to the nearest thousand. That means 3 decimals. To the nearest 3 decimals, what are each of these equal to? Okay, so I'm going to do approximate here.
Correct. Is there a? Because I put in 13 divided by 7.
Oh, press Control Enter. 13 divided by 7. Hit Control Enter. And give me to the nearest thousand. That means 3 decimal places. All right. What are y'all getting when you type that in?
For the first one, I got 1.857.
Or is that what everybody else is getting?
Yeah.
1.857? 1.857. Okay, now do the next one.
1.923.
And do the next one.
1.96.
960.
Mhm.
And finally,
Yeah, 1.9, 1.98.
980.
Yeah, it was 1.9795.
Okay, that's fine. Okay, so here's what I'm gonna do. I'm gonna ask you a question. A limit doesn't tell you what the graph is. What does the limit tell you?
Where the graph goes.
Okay, so I want you to think about this. The limit of R. What does R represent in this problem?
The ratio.
The ratio. What's the limit of R as our n values, or our x values in this case,
Increase.
as our x values increase? As we get bigger and bigger and bigger, what is true about our R?
They're increasing.
They are increasing. Do you think they'll increase forever?
No. Yes.
They're not going to increase forever. They're going to approach a number. That number is going to be the common ratio. What number does this look like it's approaching?
2.
Okay, so here's what we're going to say. We know that this is going to be some type of exponential equation where the base is 2. You tracking?
Mhm.
So now what we need to do is change our data to where each term is multiplied by 2 to get the next term. I'll say it again. Now that we found our limit, we're going to find out, okay, so what do I need to add or subtract to make this where each term is multiplied by 2? Does that make sense?
Mhm.
Okay, so what I'm going to do, use your smart pencil, right click, and just slide this over. What?
Good morning, Raider Nation. Just a brief.
Okay, so here's what I want you to do. If you have space, add an extra table. Whoops, why am I not adding? Add in an extra line here for your table. And what we're going to do is either add or subtract a number to get our base. So this will be f of x plus or minus some number. So I want you to think about what number we could add or subtract that would get these to where they're all doubling. For example, if I added 1 all the way down the list, some people might think, oh, this will work because this is now a 14, but we have a different problem.
8.
This is now 8. Is 8 times 2 14?
No.
So it's not plus 1 because that would not work. So I want you to think, what could you add or subtract by to get these doubling?
-1.
What if we minus 1? Let's try that. If we subtract 1, what do we get here?
6.
What about here?
12.
Is that working?
Yes.
Okay, so here's what we're gonna do. We're not gonna put the -1 right there. Where I'm actually gonna put the -1 is right up there. So what is 25 minus 1? Is that still working? 48. And 96. Okay, as we go to write our equation, here's what's going to be a little bit tricky for some people, is we're going to find out that when we write the g of x equation, this is going to seem backwards, but I'll show you what happens. The initial value is when x is 0. So when you go to write your equation, let me just give you one more time. Exponential's equation looks like this: a dot b to the power of x. Write down in your notes so you haven't forgotten that a is your initial. Whenever x is 0, that's what your y value is, your a. Your b is your ratio, your common ratio. Okay, so you have that written down? All right, so here's what we're gonna do. This is our g of x equation right here. G of x equals that. So g of x would be, what's g's initial value? 6 times, and then what's its ratio? What are we multiplying by? I heard Chris saying it very quietly. Everybody else, just make sure you're following. What are we multiplying by every time? 2. So the initial value is 6, and you multiply it by 2 to the power of x. Now that's g's equation. Really simple. Does that make sense, how I just wrote that? That's the initial. That's our common ratio. All right, one more time right here. This is the initial. Now this is the common ratio. Now the next part, if you do the algebra, this makes total sense. Common ratio. Now we're going to write the equation for f of x. Do some algebra here. If I want to get f of x by itself, how do I get rid of this -1? I need to add it. So f of x, I'll write it one time by algebra, and then we'll actually write the equation. F of x will equal g of x plus 1. Did you see how we just got that? How do we get f of x isolated? You would add 1. So what I'm going to do is now is just plug in the equation and add 1 on the outside for my final answer. So it'll be f of x equals g of x is perfect, 6 times 2 to the power of x, but then I add 1 as a vertical translation, and that's my table right there. But that would give me my equation. Okay, we're going to test this. Sorry. To test it, we're just going to go to graph. We're going to type it in there and then press Control T and see if if the table and the calculator matches this original table they gave us, the original table, not the one we created, but the original table. Okay, so let's go to our calculator. Add a graph. The equation was 6 times 2 to the power of x, and then we're going to add the 1 on the outside, plus 1. Hit enter, and then hit Control T. I'm going to go up 1 value so I can see 0. Was this my original table that they gave us?
Yes.
Yeah, it worked. Where did my screen capture go? There we go.
How to get the, because we subtracted 1 from that side.
Yep. So that's the part that some students are probably going to have a little confusion on. But if you think through your algebra, it makes a lot of sense. If you're not thinking about algebra, it'll seem confusing to you. The way I got that is right here. We have f of x minus 1, but we want to get the f of x isolated. So just think through your algebra. What's the opposite of subtracting 1 to get f of x isolated? Adding. And so that's why over here we had g of x plus 1. I just did the algebra there. We added the 1 to both sides. So then we had g of x plus 1 is equal to f of x. So then all you did is take g of x, add 1 to it, you got your answer. Yeah, go for it. Any other questions on number 1 before I move on? All right, let's reload and try it again. Same instructions. Let's look at this one. Let's figure out what's approximately happening each time. What does it look like it's happening going from 2 to 10? Looks like it's multiplying by 5. Does the next one get multiplied by 5? No, it gets multiplied by 3.4. Okay, what about the next one? It's getting close to being multiplied by 3, right? So here's what we're going to do. We're going to test this out. Let's say, let's start with the last one. What's 322 divided by 106? Is that approximately what number? What are you saying, Audrey? I hear you. Okay, as x approaches infinity, we're saying we think this might be going to approximately 3. Is that what we're saying? We okay with that? All right, let's add a table line. Let's add a line to our table. They call this one g of x. So this time I'm just going to say f of x equals g of x. And now we don't know. Okay, let's start thinking through if we multiplied here. If you multiply by 3, do we get 10? No, so we either need to add or subtract a number. And by the way, your A, it needs to be a positive number for this to work, unless they're alternating. So it needs to be a positive number. So the most we could subtract is a 1. Can't be 0, can't be negative. The most you can subtract is a 1, but you could add if you want to try to get a number that would work. What do y'all think?
Add 2.
Okay, if we added 2, let's check that for a second. What do we get here? 4. This would become 12. What would this become? Is that working good?
Yeah.
Yeah, that's going to be our equation. So we're going to say it's g of x plus 2. So 2 plus 2 is 4. 10 plus 2 is 12. 36. 108. And then finally, 324. That would work. Okay, in this case, what is g of x's equation? I'm sorry, what is f of x's equation? The one we just wrote? What's our initial? Initial is now 4 times, what's our rate? To the power of x. Good. So now let's write our g of x equation. So to get the pattern, that we just wrote that equation for the transformed graph. So now let's rewrite our equation for g of x. So if we did our algebra, g of x is being added by 2 to get f of x. So how would I get g of x isolated? It's going to be f of x minus 2. So g of x would equal 4 times 3 to the power x minus 2. And there's your equation. So you starting to understand how we write a model for exponentials? All right, Anthony. Pajama day, and I think that means we can take naps. Take naps in English. I give you permission. That's right. All right, let's look at the next one. What appears to be happening right now? Would you guess? What would you guess is the limit this time?
0. Something lower than 1. Going to negative infinity.
It's not actually going to negative infinity. Oops. I did habits. I did limit of f of x. Let's do the limit of the ratio. What do you think's happening to each number? So 63 is becoming a 31. 31 is becoming a 15. 15 is becoming a 7. 7 is becoming a 3. It's almost half. It's almost half each time. So let's go ahead and test. What if our ratio is going to be 1/2? That's what we think it's going to be. It looks like it's approximately a half each time. Now, actually, I think this one, and I would need to write this properly. I think you would need to say it's the closer you get to 0, the closer it is to 1/2. So the farther away, it won't be looking as much like 1/2. I think so. We might need to put this as a 0 plus in a moment. We'll test, or y'all go ahead and tell me in the calculator. We'll figure out real quick. What is 31 divided by 63 as a decimal? That, what I'm trying to say is that might be the closest one to 1/2.
Yeah, 0.198.
Sorry, approximately it's how much?
0.92.
492. Okay, now let's do 7 divided by 3. Something tells me this is not going to be as close to 1/2. Oh, I did that backwards. Sorry. 3 divided by 7. One more time. 3 divided by 7.
Yeah.
428.
Yeah.
Okay, so the first one was closer. Yeah, so let's change this to make it proper. Do 0 plus. The closer and closer we get to 0, going from the positive side, going from the positive numbers, the closer we get to 0, the closer the rate is to 1/2. Okay, so now that's corrected. Let's go ahead and add to our table like we've been doing. Let's add that extra column. We want to know f of x is going to be equal to h of x plus something or minus something. If we add 1, you want to try that? What do we get? 64. Okay, is that working? And I bet the others do as well. Add 1 here. We're adding 1. 16, 8, 4. Perfect. So let's write f of x equation. This one right here. This column is f of x. F of x equals, what's our initial? 64 times 1/2 to the power of x. Now, f of x is the same thing as h of x plus 1. So h of x would be the same thing as, let's do some algebra. How do I get h of x isolated here? Subtract 1. It'll be f of x minus 1. So f of x is 64 times 1/2 to the power of x, and then we subtract 1 on it. And there's our equation. Questions on how I'm doing that? So now we're learning how to write a model for exponentials without using a calculator. Before I go on, I'm just going to make this infinity symbol look a little bit more like an infinity. There we go. Okay, so moving on. So when you are modeling exponential functions from data, we can write a model if we're given the common ratio and the initial value. So said this way, you're given your R and the initial value. What letter we use for that? A. Or two input-output pairs. We can find the initial value and the base common ratio with these two pairs. Now, Delta Math usually does number 2. Right, so I was looking through a lot of their problems. I did a whole lot just to kind of get an idea what you're doing. And it seems like to me they give you these two input-output pairs. That's what you're gonna get used to. So on this next one, that's what I'm planning on doing here.
Oh my God.
Oh my goodness, you have to read. All right, for t, excuse me, for 0 less than or equal to t, which is less than or equal to 30 minutes. So time is somewhere between 0 and 30 minutes. The number of fans inside a large sports stadium can be modeled by the exponential function there, where f represents the number of fans inside the stadium t minutes after the doors open. There are 47 people in the stadium 2 minutes after the doors open, and there are 2,602 fans in the stadium 20 minutes after the doors open. Use the given data to write 2 equations that can be used to find the values for constants a and b in the expression for f of t. Okay, so this time we're not actually even supposed to solve. What does it ask us to do?
Make an equation out of the letter.
Okay, so let's talk about this first. What's the first coordinate point they give us?
They give us 47 and
47 and 2. Now is 47 the number of fans or the time?
fans.
Fans. So this, we'll call this is f of 2 here. Because 2 is time. So when time is 2, we have 47. You follow so far?
Mm-hmm.
And they give us a second point.
20 and 2000.
2,602, is that the fans or the time?
Fans.
And this is f of 20. Fans at 20 minutes. So at 20 minutes, we have 2,602. I'm going to drop the comma on this one so we don't get confused as the coordinate point. So that's 2,602. Now, this problem is only asking us to write 2 equations. It's not asking us to even solve for it. But what do y'all say we go ahead and do it anyways? I'm going to plug these in. So here's what I would have. If you plug these in, does 2 go into place of f of t, or does it go in the place of t? T. So you could rewrite this as an equation. You would say 47, that's f of t, equals a times b. I'm going to drop the parenthesis here. To the power of, what's my t? 2. And then over here, I could do the same thing. 2,602 equals a dot b to the power of 20.
That's it.
Now that's all this one asks us to do. Is there a part B?
No.
Delta Math, you're probably gonna solve a few of these. You want to solve?
No.
Okay, so here's how you would solve this. It's quite simple. I heard no, so I'm gonna do it.
No, even if we said yes.
What is exactly, there's 2 values that are exactly the same in these 2. What are the 2 values that are exactly the same? A and B. What I'm going to do is I'm going to solve for A, just because it's going to be easier to isolate and have A equaling A. So over here, if I solve for A, and then we'll substitute, that's going to be the plan. If I solve for A right here, how do I get rid of this times B squared?
So
Okay, we're gonna divide by b squared. So we have 47 over b squared equals a. No, a is not squared. A is just a. So now you know what we're gonna do? Now we'll substitute. We're gonna take this over here and we're gonna substitute. Substitute. So now I have 2,602 equals, instead of a, what can we replace it with? 47 over b squared times. Okay, now we can simplify that. So this is the same thing as b squared divided by b, excuse me, b to the 20th divided by b squared. What do we learn about exponential rules when this is the quotient property? I'll let you see it this way. That's b squared there. What do you do to the powers? You subtract. So this will be 47 times b to the 18 right there. That was the quotient property that it just did. Quotient property. Same base, we subtracted. Okay, now to get b, what would I do? How do I get rid of this 47 to get b isolated? I shouldn't say b isolate, b to the 18th. Wait, I heard subtract. Am I subtracting? That's multiplication. What's the opposite of multiplication? Division. Okay, take 2,602 divided by 47. What do you get? Simple algebra. Simple algebra. Simple algebra. Get some 14-year-olds in here. Simple algebra. Are you getting what number are you getting? Okay, how about this? How will we get b isolated if it's b to the 18th? Not square root, but 18th root. All right, let's see. Do you get a good value if you say the 18th root? B will equal the 18th root of 2,602 over 47. Does that give you a good number? Anthony, that's not your calculator. Does that give us a good number, or is it still a bad number? $1.249. Now is that exact or is that rounded? I mean, is that a terminating decimal 1.249 or is it still continuing? What'd you say? Okay, so we're just gonna say it's not a good number. We'll round it. So to the nearest thousandth, what are you saying the value is? 2.4. Wait. To the third decimal, what is it? 2. Okay. I'm getting frustrated. I'm hearing a couple different people saying, why am I not hearing like 30 people? It'd make it a lot easier if I was hearing 30 people say the same thing. All right, so you should have typed this in by now. What are you getting? 1 point. Okay, 2498. So what does that become? 1.25 with a 0. That's what we're gonna round this to. Okay, so once you have your B, how do you think you could find A? Plug it in. And so I'm gonna take this all the way over here and I'm gonna plug in. And if you wanted to find your A now, what you would do is 47 equals A times 1.25. 1.25 raised to the power of, I'm dropping the 0, raised to the power of 2. And so what's the only step left to solve this one? You would divide by 1.25 squared. Now, why am I dividing? Tell me some algebra. Why am I dividing? I want A isolated. A is multiplying. The opposite of multiplication is Okay, and so now type that in the calculator to see what A is. We'll go to the nearest thousandths again.
30.08.
30.08. So 080 is what it rounds to be. 30.080. And so those would be our values there. So we have one answer over here. Now again, this problem didn't ask us to solve for them, but that's how you would do so. Because you're going to have to do that on Delta Math. I just wanted you to see it. So there it is. All right, wake up. All right, let's look on to another one. Again, what did I give you this time? Did I give you the initial value? Did I give you a common ratio?
No.
No, what did I give you this time?
Give me two. You gave me
I gave you two random points. So it says the selected values of the exponential function g are shown in the table above, where g of x equals a times b to the power of x. Use the given data to write two equations that can be used to find the values of constants a and b in the expression g of x. Okay, so let's do this again. If that's x, that's y, x, y. What would be my first equation I could use?
It'll be 21.54 is equal to a times b to the power of 3.
It's 21.54 equals. Do we know what a is?
No.
We don't know our initial. Do we know our common ratio? Sure. We don't know our initial. We don't know our ratio, but we do know it has a power of 3. There's one equation. What's our other equation?
3.62 is equal to a times.
Will this be exponential growth or decay?
Okay.
It will be decay. That's good. It's getting smaller. Okay, so it says find the values of a and b. So this time we are actually supposed to do it. We're not just doing it for kicks and giggles. We'll do it because we're commanded to do it. How can we solve for a and b?
Alright, so you simplify the first equation. So you divide both sides by b squared. B to the cube. Alright.
Okay, so what you do is if this is pure algebra here, if you have two unknowns like we do, what are our two unknowns, Abigail? Just make sure we're tracking. A and B. Those are our two unknowns. If you have two unknowns, to solve it, you have to have two equations. If you had three unknowns, how many equations would you have to have? 3. If you had 4 unknowns, how many equations would you have to have?
4.
4. That's how it works. We have two unknowns, so we only need two equations, which we have. So we're going to say A is equal to, let's isolate here. How would you get A by itself?
Divided by b cubed.
Okay, 21.54 divided by b squared or cubed? B cubed. And now what do we do with this?
You plug it into the second equation, so it's 3.62 is equal to 21.4 divided by b cubed times b to the power of
21.54 divided by b cubed times b to the power of 8. And now we can do the quotient property again. I have the same base being multiplied b to the power of 8 divided by b cubed. So if I do the quotient property, again, so here we isolated the a, now we substituted. Let me go ahead and write in substitute. That's what we did here. We substituted that in. Quotient property, we could simplify this equation. 3.62 equals
times b to the power of 5.
b to the power of 5. Great. Come on, Jonathan.
And you divide by 21.54 both sides.
We're going to divide. Why are we dividing?
Because
Asif, why are we dividing? Why are we dividing? We do need to divide to get b to the 5th isolated. Why do we divide though? What's this 21.54 doing to the b to the 5th? It's multiplying. What's the opposite of multiplication? Division. So we'll do the opposite here. 21.54. Whoops, 21.54. And then the last thing we'll type in our calculator. How do you get b isolated? It's b to the 5th.
square rooting.
Square root it?
No, not square root, but root it.
Fifth root it. All right, so it's going to be the fifth root of 3.62 divided by 21.54. I'll let y'all type that in the calculator. .6999. So we can round this to be approximately how much? Is it 0. Just 0.7? Is that round to the nearest thousand? Okay, so 0.7. So how do I come back and now find the A? We plug it in. So now I'm going to plug back in over here. I'm going to take this right over here and plug it in. And you can use any equation. I'm going to use the easier one, the more simple one, this first one. We're going to say 21.54 equals A times 0.7 raised to the power of 3. How will you get the A? How do I isolate this A right there? We're going to divide that by 0.7 to the power of 3. 0.7 to the power of 3. And I'll let y'all type that in all at once there to give me my A. Honestly, I should have done an approximate here since that was a rounded value. I should have done approximately there.
It's 62.7988. Oh, you want it rounded to the nearest 10?
Nearest thousand.
Thousand.
3 decimals.
8. Yeah, 62.8.
62.8?
Yeah.
62.8. All right. Great job.
Wait, no, 1,000?
That would be 3 decimals. So it'd be
Oh,
0,
my
0 after.
62.799.
7.99 or 62.8.
62.
Let's just leave it. Let's just leave it. Close enough. There we go. So those are our 2 values there. Questions on how we did that? Think you can duplicate it?
Yes.
I hope so. Because you're gonna have to.
I looked at that.
All right. Oops, sorry. Going too fast. All right, we're about to see something I gave you by formula on lesson 2-1 or 2-2 where we did the money. Do you remember that? Yeah. APERT and all that. We learned about some investments, how it works with houses, how it works with credit cards, all that. Yeah. Are you good? Move on. Okay. So it involved the number E. So E is approximately 2.718. E is if you think about it, it's like pi. If I said pi, what is pi?
3.15.
So I'm just gonna say 3.14 right now, because that's how most people know it. But I'm gonna do approximately. Does pi ever change?
No.
Do you know where pi comes from?
22 divided by 7? Circles.
It is circles. Where does it come from in a circle?
Circumference.
Similar. Y'all getting pretty close.
Circumference.
It is. It has to do with the circumference of the circle. That's right. We'll figure that out later in the year. I'll show you. What do I want to say? E is similar. It's the same thing. Is E going to change?
No.
No. But we're going to use it. E is on the left side of your calculator. We're going to use that button frequently. Okay. So example 4. The number of bacteria B in a particular culture can be modeled by this exponential function.
APERT.
Okay. If this were APERT, what is A?
Your initial value.
Okay. Or no, it'd be the final value. What is the P?
Your initial.
That's your initial 17. What's this 0.31?
That is your ratio.
That would be your ratio right there. It's a 31% growth rate, where T is measured in hours. Let A equals A dot B to the power T be an equivalent expression for B of T. Find the value of A. So it says here, find the initial value. So now we're converting it. We're going to change this equation. We're going to get rid of the E. What we're going to do, I'm going to explain to you, is we're going to exchange this right here, this section. we're gonna find out what is this in terms of b to the power of t. Does that make sense? So what is our initial? Our initial will not change. That's here. This is saying find the initial value. What is our initial value?
17.
Okay, so A equals 17. Sorry, when earlier, if you were referring to that, I was talking about PERT. This A would not be 17. This would be capital P. But in this case, A is 17. Sorry, I didn't realize what you were saying. Find the average rate of change, B of T, over the interval from 1 to 7. What I'm actually going to find, it says average rate of change, but what type of equations are we dealing with? Exponential. There is a formula for this. If you can get this. All right, you ready? Average rate of change. We learned that early in the year is the change of y over change of x. If you want to find your ratio, though, I'm going to give you this formula because I think you can memorize it. If you want to find your ratio, here's how you can do it. The ratio will be equal to the change of x root of, you could do, I'm going to do y2 over y1 because I don't know how to write that as change of y divided by change of y or whatever. So I'm going to do it that way, y2 over y1. So what am I saying for this problem?
So you want to find your two, both, so you would plug in 1 and 7 into that equation.
That's right.
Take those two values, divide it. And
So-
then you do 7 minus.
All right, let's slow it down just a little bit. Let's plug in a 1. Let's find b of 1. I'm plugging in a 1. This would equal 17 e to the power of 0.31 times 1. All right, do you see what I just did there? Okay, go to your calculator, press enter. Type that in, just press enter. Don't type in b to the first equals. We're solving for b. B is isolated, so just type in this part. 17 times e to the power of 0.31. What's anything times 1?
1. I mean itself, yeah.
Not 1, but itself, yeah. So just type 17 times e to the power of 0.31. What do you get? Let's go 1,000, 3 decimals. 23.17. Is everybody getting that number?
Yeah.
We're in agreement so far? All right, now we're going to find b of 7. So what's different this time? If you'll take, you can just copy what you did, but instead of doing 0.31, it'll be 0.31 times 7. $148.891. Okay, so now what I'm going to do here is I'm going to plug these in, and here's what we're going to. I'll show you an easier way in the calculator to get the exact answer. What I'm going to do is this: the change of x. How much? In this case, it's the change of t. How much did t change from going from 1 to 7?
6.
What we're going to do is take the 6th root of what's our second y value? 148.891. 148.891, and then we're going to divide that by the first, which is
43.
okay. And to get an exact value, I'm going to actually pull up my calculator this time. I'm going to show you how you can type this in. If you graph this, or if you type it in as a function, here's the way to get the exact answer. I'm going to type this in as a function and graph. It was 17. There's their E button to the 0.31. Because the calculator uses X, I got to put an X there. Once I type that in, I can add a page. And I should be able to get, if I do F1, that's my function I just typed in a 1. I get that first answer y'all got. Was that the value you had? Yes or no?
Yeah.
I got it right. And that was your second value? Okay, to get an exact answer, you can do it one of two ways. You can do it like I did, and now you can do the 6th root. So press Control Power, that button right there. Put the 6th root. And then inside here, do a fraction. What you can do is you can go up and copy your answer. You can hit Control C, and you could copy that answer. Hit Control V, and it'll paste it. So you get an exact value. Except I pasted that in the wrong spot, didn't I?
Yep.
Where's that one supposed to be?
No, it's supposed to be on the bottom.
That one's supposed to be in the denominator. So I could paste it here, or if you typed in like I did, you could do F1 of 1 right there. And it would substitute it for us. But I'm assuming most of y'all did not do it that way, so I'll just paste the number. Control V. So there's that number. And now we take the second Y. I highlight it. What in the world just happened? Okay. I highlight the number. I'm gonna hit Control C. That copies. And then I'm gonna come over here and hit Control V. I'm gonna get an unrounded answer. All right, press enter. What do you get for your ratio?
1.3634.
All right, so we're gonna go to the nearest thousandth. So we're gonna say this is stay as a 3 or is it round to a 4?
Stays the 3.
Stays as a 3. Okay, so here's how we'll write. I'm gonna take a picture of this over here. Actually, I'm not gonna paste it yet because I want to put a new one in. Here's what we just found out. This ratio, this is what I want to write. The ratio is 1.383. I already forgot. What's your calculator say? Jonathan. Jonathan. Pick up. What's our ratio?
R is equal to 1.363.
363. 363. Let me do approximately. Now I'm going to come back to this in a second because, and I'll just do it here. Here's what you're going to have to do in delta math is you're going to have to rewrite it. And it's going to want you to write it in terms of a times b to the power of x. We just found our ratio, which is the same thing as b. We just found a new rate. You could rewrite this equation as a of t equals, what was our initial value? 17. And we just found our new base of 1.363 to the power of t. Now, why might this be helpful? Because now, what was our power over here?
0.31.
0.31. What we just found out is that's the same thing as 1.363. Some of you are like, wait, what? We just did a lot of work for that? Yes. If I typed in e to the 0.31, what do we get?
1.
So I walked you through all that to show you how you could simplify this. Okay, because this is, I know.
What didn't you do? Okay, so.
Okay, because you wouldn't have understood what I was doing.
You just wanted to rewrite.
All
the
right,
equation.
so now we should get the same answer regardless of how we write it. It says find the value of t when the number of bacteria in the particular culture is 1,000. Where would that 1,000 go?
In the T. Oh,
Nope.
no, it's the
You can say it's the capital A or the capital B, regardless of which equation you're using. So you could use, if you're using the first equation, you would say 1,000 equals 17 e to the power of 0.31 t. Or you could say 1,000 equals 17 times 1.363 to the power of t. Either way, we have to solve for t. Now, y'all haven't learned how to do this yet. Haven't taught you. So we are going to insolve this. Go insolve either one, whichever one you want. We should get the exact same answer. So menu 3, 1. I'm forgetting my numbers already. 1,000 equals, which equation y'all want to use? The original or one we just came up with? Original. 17 e to the power of 0.31 t. And we'll do a comma t. Press enter. How much time does it take for the bacteria to grow from 17 bacteria to 1,000? Is bacteria when it's plural bacterium? What is the word for that one? Still just bacteria? All right. So those are all the values we need here.
Do we graph the nearest hour or?
Let's just say 13.1 hours. That we'll do that. 13.1 hours. And now I'll copy this over for us, all of our equations.
So instead of doing all that math, you could have just done.
That's how you could have done it. Yep. So I showed you the way. I think Delta Math is going to show you. That's what they're going to walk you through.
So
Okay.
can I just do E times the ratio and get minus B?
I'm going to say approximately 13.1 hours. It wasn't hours, right?
Yeah.
I can't see. Yeah, T is measured in hours. Okay, what was your question?
Couldn't I just do E times my ratio to get my B?
Absolutely could.
Okay.
It'll work that way. By the way, if you were given a table though, not an equation, this, what I gave you right here, will work. So that's how the average rate of change works with exponentials. It's instead of being change of y's over change of x's, it's the root of the change of x's. Change root over y2 divided by y1. However you say the change of y's in there. That's how it works differently. Okay, that's how you find it from a table. Yeah. Okay. So now, example 4, the number of bacteria. What? Isn't this what we just did?
What? Yeah.
Okay, I don't know why I didn't change this to a C and a D. Sorry. Let this equal that. Find the equivalent. Okay, so we just did this. Here we go. Let's fill it in. So it's saying find an equivalent expression. We already did this. What is the equivalent? Is A of T equals 17 instead of E? What do we change it to? 363 to the power of T.
What's this find value?
Okay, I'm confused with what I'm doing here. I have no idea what I was running right on here. G of x equals f of x to the -3. I don't remember what I was doing that. Let's just scratch that out for now. Something tells me that was just supposed to be part C, and I forgot to delete that probably from the previous slide I copied. Just leave it like that. This is part C. All right. Example 5. After 50 deer were introduced to a large wooded area, the population of deer in the wooded area can be modeled by the exponential function d of t equals a dot b to the power of t, where t represents the number of years since the deer were first introduced. The population of deer increased by 13% each year. Hey, do you know what that's telling you right there?
That's a ratio.
That's the ratio. So the rate of growth is 13% is the same thing as, okay, now what did I give you here?
B
Not B,
or A?
that's A, the initial amount. So if you remember at the start of class, I told you there's 2 ways you can write it. If they give you the initial and the ratio, you can write an equation, or if they give you 2 points. So if we're going to write an equation, since they gave me these 2 values, I can write an equation. D of t, the number of deer, would equal, what's our initial? 50. Now, if the rate is 0.13, how that actually goes in the equation as a base is it's going to be 1.13 because that's growth. So what I'm trying to say is as a base, that's the ratio, the common ratio. As a base, that is, the base would equal 1 plus or minus r, depending on if it's growth or decay. So if it were losing 13% a year, you take 1 and subtract 0.13. Does you follow what I'm saying? So it'll be 1.13 to the power of, what's my independent variable this time? T. There you go. There's your equation. Now, you're just gonna sleep. Get out. Part B. According to the model found in part A, what is the population of deer in the large wooded area after 6 years? So what is 6?
The time.
Time. All right, let's find out how many deer would be there. Any takers on the guess?
Let's do it. So it's 1.13. I don't know. 75. Like 70. Yeah. So that's the 75.
That's a great guess. I think it's gonna be closer to 100. I'll tell you a shortcut I know. Type that in, see what you get. I shouldn't have said D of T there. I should have said D of 6. So the deer after 6 years would be 104. Okay, there's a rule. You'll learn this if you take financial classes for investments. The rule is 72 with compounding interest. With interest, it compounds. They talk about that. That's why I'm switching to money here. If you take 72 and divide it by your rate, you have approximately how long it takes for it to double. Now, the numbers as they turn out, how many times can 13 go into 72? Do 72 divided by 13 real quick. What do you get? It goes in 5.
5.5.
So 5 would be 65 with the left. And then this would go in again. 5. It takes 5.5 years for it to double. That's why I knew it was going to be around 100. Because I was just going off that. I knew it was going to be about almost. I knew it was going to be a little bit less than 6 years to get double. That's why I said that. So that's the rule. If you're wondering, how long does it take something to double? You're going to learn that. And that's how they talk in financial circles. How long would it take for my investment to double? And they use the rule of 72. You divide your interest rate. So for example, what if you had a 7% interest rate? How long would it take for your money to double if you invested in a 7% interest rate? Well, you take 72. You take 72 and divide it by 7. And it's approximately what amount when you take 72 divided by it's around 10 years. It'll take just a little bit more than 10 years for your money to double if you're getting 7%. That's what the rule of 72 is. So that's how I knew it was going to be a little over 100. All right, let's go to part C. Find the time when the population of deer in the wooded area, like a hotel inn, is expected to reach 5,000. Okay, what did I give you this time?
The final value.
Okay, so 5,000 equals, what was our initial amount? 50 times 1 point to the power of t. Now, you can just solve this. If you're doing it by hand, you divide by 50. And 0 cancels, and 5 goes into 500 how many times?
1.
So this is what you're actually solving, 1.13 to the power of t. And there is a very simple way of doing that. Yep. There's a simple way of doing that, but we haven't learned it yet. You'll learn it just a few more classes from now. Go ahead and solve that. What do you get? 37.68 years. Okay, so now let's think on this for a second. If we were going to change this to months, what was our equation in years again?
In years.
So this one says write an equation where it's measured in months. So in years, D of t is 50 times 1.13 raised to the power of t. Now that's in years. So let me break this down, and I'm going to use the money equation. I don't know if you remember that one of the money equations I gave you was you take your principal and you do it 1 over the rate, the number of times it compounds per year, raised to the power of nt. Do you remember that formula?
Yeah.
Okay, that's the idea here. What you would do if we were going to change this to months, we're going to say n is how many times in a year is a month? 12. So what's going to happen is we're going to take our equation, and what's our rate that we were working with before? I'm going to call this m of t. Any ideas why I'm calling it m of t? For months would equal 50, and we're going to do 1 plus, our rate was 0.13. I'm going to divide that by 12, but then on the power, it becomes 12t like that. Make sense what I'm doing here? We could leave it like this, but we could leave it. I'm not. Let's simplify that. What do you get when you simplify? Just do 1 plus 0.13 over 12.
1.13 divided by 12.
Yeah, because I'm sorry, 1 plus 0.13 divided by 12. What do you get?
1.13. 12.1. Wait.
Should be 12.1. Let's try this. So
is it because you didn't have the 1?
0.13 divided by 12. You can't add 1 into that because it doesn't have a common denominator. So it's 1 plus, or you could do it 12 over 12.
Yeah.
So it's 12.13 divided by 12. That would work. 12.13 divided by 12. I'll do that. I'll show you 12.13 divided by 12. Whoops, divided by 12. That would be a common denominator. 12 over 12 when you add. That should give you the same answer. Okay, we're gonna say this is approximately 1.011. So this is about 1.011. 1.011 raised to the power of 12t. That's how you could change it to months. So today you have seen us more and more changing bases, doing vertical translations. We've done a lot of different things to our equations today. A whole lot of different things we hadn't seen before. Questions over what you saw me do here?
Hold on.
Oh,
You put 0.13, so that's the percentage ratio.
that's the rate, but here's why. Because before it was a rate per year. It was 13% per year. But if you're changing it to months, it's not going to be 13% per month. 13%, 13%, 13%, 13%. If you do it for 12 months, it's going to be a whole lot higher than 13% over a year. So what you do is you take your 13% and say, what is that per month? And so that's what this 0.13 is divided by 12. That's getting the percentage per month. Percent of rate growth per month. Does that make sense? And then because there's 12 months in a year, you had to multiply the t times 12. So if you did 2 years, you don't want that number to be a 2, you want it to be a 24. That's why I multiply by 12 there. If that makes sense. Okay, actually, wait, there's one thing I'm now thinking about this. If we were going to plug in months, we would need to reevaluate that t. Hey, I have this. This is still in years. I'm sorry. This is still years. You know how I just realized we didn't solve it for the month. For example, if you gave me 2 years, that would work right. How many months would it be? You could multiply. What's 12 times 2? 24. If you wanted to do it as a plug-in by months, though, if you want to do it as a plug-in by months, let me go back. If we want to do it by months, t is equal to how many months?
So we should divide instead.
Like that, right? Is that correct? If you had 12 months, that's equal to. So hey, hang on. That's still years. I just broke it down to a monthly growth rate. That's not what we're looking for. You would just do it this way. D of t, I'll call it d of m, would equal 50. This is the easier way of writing this. 1.13 to the, instead of t, what is t the same thing as? T is equal to m over 12. It would be like this. That's if you want it in months. I'm sorry.
So you overcomplicated.
I overcomplicated. This is in months. What I did is I wrote the monthly. I changed it to where you saw the percentage per month.
Gonna write down monthly.
This is like you stick this with stuff and not with money.
Yeah, some of the stuff exponentials get confusing. I'm not gonna lie. You know, all the little different rules. It's not like linears where everything makes sense. Some of it gets confusing, but that would be the equation where you change the t to a months divided by 12. Okay. You have some DOLs. I want you to practice here. See how many did I give you? Oh, just this one.